science is humans' way of understanding nature. Science is also about the methodology. You make hypotheses, you collect data. Now, there's another part that most people talk about. So what's good is science? If I just understand science, what good does it lead to? If you don't understand something, you cannot benefit from it. And without that knowledge, that understanding, you'll never be able to cure diseases, advance human civilization. So I think science is a very important part of human civilization.
As the world moves from poverty towards sustainable wealth, the growth in energy demand is frightening. We do need to be thinking as scientists and engineers about how we help. We know that we want to basically be using renewable energies for all of our energy demands. The real question is, how do we get there and how quickly can we get there?
لكون العالم يواجه الكثير من التحديات، فهناك علماء يسهرون الليالي محاولين إيجاد حلول لتلك التحديات، متسلحين بالمعرفة والخبرة والشغف والأمل. تدعمهم الجامعات الرائدة في العالم. لقد جئنا لاستكشاف إحدى هذه الجامعات على الساحل المذهل للبحر الأحمر في المملكة العربية السعودية.
We are a research university. In other words, we are not a comprehensive university.
KAUST was established as an institution to address global challenges, and energy is one of our pillars, one of the areas in which we were set up to work. And so we have a wide range of research activities that are addressing energy. Those research activities go from more traditional energy sources all the way through to the very latest renewable energy sources.
Energy is everywhere, and it's just about how we capture it and use it effectively. My dream is decentralized energy. Everybody can have access to energy and electricity, right, in the world. And you're seeing the sun is shining every day in our lands, and how come that's not possible? I hope I can see those days that it's decentralized and can reach to every household, and that motivates me every day.
تعرفوا إلى داريا، أستاذة في جامعة كاوست، ستتحدث عن أمور تثير اهتمامنا.
Energy harvesting is one of the beauty of science. The technology that we developed, which is transparent photovoltaics, is actually utilized in several different platforms, complementary to the existing silicon photovoltaics. You know, we cannot replace silicon. It's very good technology, and it's going to be on the land, it's going to be on the roofs, but we still need more energy, and we need to start building our energy resources. And buildings, as you see here, are one of them. Glass is one of the mostly utilized cladding material, and with our transparent photovoltaics, we can turn these buildings into power machines, we call. So we can generate electricity from the windows, or actually even put them on the facades that you can keep generating energy and electricity from the sun. One day in the lab, when we were developing new type of materials and devices, we made the cells and we were looking at it, and we were like, hold on, this is so transparent. And then all the things actually untangled there. We were thinking, this is very important, and we wanted to scale that transparent photovoltaic technology, and we could use them in the windows, in the glass, where we could actually laminate. And because these materials were transparent, they were absorbing in the near infrared. So for instance, when you stay here, you have the light coming from the sun, but you also feel the heat, right? You feel warm. So our technology just lets the light in, but you still feel cool. And in the meantime, another KAUST-born startup, Red Sea Farms, were working on greenhouses and actually trying to keep them cool as well. And one day when we were having a chat with Ryan, the CEO today, I told him, Ryan, we have an interesting technology, glass, that we could actually block the heat and then he was like, Daria, this is amazing, that's enough. And I was going to say, we can generate electricity as well. And then he was, wow. So that's actually how we merged afterwards. And today we do all these technologies under the Red Sea Farms umbrella.
So power glass is a really important part of the complete system, especially as you think about controlled environment agriculture in hot climates. So controlled environment agriculture was designed in northern climates where we want the heat to get in because it's part of the sustainability of the process. It keeps the greenhouses warm in the winter. But in climates like this lovely climate, we need to keep the heat out and we have to do cooling. So one of the things that the power glass really contributes to is both keeping the heat out, which is something, remember when you first came to me, I was like, stop there, that's amazing. Let's keep the heat out. But then also the heat that does get in, or any heat that we do build up, we still have to do some aspect of active cooling. And so by having a roof that both blocks heat and generates energy, that energy can power the cooling system. So you get this complete solution for maintaining an environment that's really good for the plants.
Yeah.
Because it's the temperature they want, they're getting the light that they need. Yeah, they're just flourishing inside that.
And we're not using as much fossil fuel-based
Well, that's
energy.
right. I mean, so you end up with a system that's really standalone. And that's the whole goal. And sustainable because it's standalone.
Yeah.
So you can put it anywhere, you can drop it anywhere.
And to be able to tune the molecules to absorb the stuff that's doing damage to the plants and then leave alone to transmit into the greenhouse the stuff that the plants want. That really is. It's different to anything else. People would talk about, oh, we've got heat blocking films, but they're also light blocking. You know,
That's
and
right.
they're sloppy or floppy, if you like. You know, so they absorb in the infrared, but then they absorb a lot in the infrared, but they still absorb quite a bit in the visible. Whereas Daria's she's tuned it with a sharp edge, and that is a breakthrough.
That is a breakthrough as a scientist. What we're doing here is we're making you a solar cell in 5 minutes, basically, because we can coat these layers in air, and our devices consists of several different layers. So Daniel started with the most important one, let's say, which we call Photoactive Layer. And Jules here will coat the transport layer that will help us to actually extract the electricity or charges, technically, and then we can see that it's working in terms of electricity generation. This is just an example of how many different substrates these materials can be coated or printed on. For instance, this is a flexible base that we coat our photoactive layer, and you can make transparent solar cells. And here is the beautiful inkjet printing. This is a little different than the blade coating that we described before. So this is to create 2D patterns. Basically, you can make your solar cell in any shape. So if you have your actually marine turtle, Daniel, we can even show that. You know, we are on the shores of Red Sea, and the first scientific paper we published actually was on flexible solar cells, and Daniel made them in a marine turtle shape because we have a really good marine science department here. I thought they would like them. That is in the shape of a marine turtle, and then we did the electrodes, and you can make a solar cell out of it. This is one of the unique areas you can see in your life as a facility to measure solar cells. All these glove boxes actually designed so that several people can work here within this special environment. So today we're actually sharing one of the state-of-the-art organic photovoltaic solvents that can be scaled up and used without harming the environment. And Daniel managed to have around 13.8% of the incoming light is converted into electricity. And just to give you an idea and comparison, the silicon itself is you find about like 20 to 23% nowadays. But considering all the advantages of these materials, how lightweight they are, how flexible they are, and how functional they are, where silicon cannot operate, this is actually amazing.
بسبب وفرة الطاقة الشمسية، فهي تعد بديلاً محتملاً للوقود الاعتيادي القائم على الاحتراق. دعونا نرى كيف يستخدم العلماء في جامعة كاوست التكنولوجيا لزيادة كفاءة وقود الاحتراق النظيف وتقليل تأثير ثاني أكسيد الكربون على البيئة.
I think that we all will agree that combustion cars have an end date. I don't know if it is going to be in 20 years, in 30 years, but there will be a future in which we will go electric on one hand, and I believe hydrogen in a far bigger percentage.
The world is facing many energy-related problems, and my role as a scientist is to ask the questions, find the right answers, the honest answers, the true answers, and as a university professor, to help others to do the same thing, because it's not a one-person journey that's going to solve the problems of humanity. It requires all of humanity to come together and many people to become educated, knowledgeable, and inquisitive about how to solve the problems. So we're here in engine test facility. And what we do in these types of engine test facilities is develop new types of fuels. Fuels that will allow the engine to operate more efficiently, and fuels that will result in lower emissions of carbon dioxide, greenhouse gases to the environment, but also lower other types of harmful pollutant emissions. And the way we do that is by taking renewable energy, wind and solar, converting that to hydrogen by electrolysis, and taking that hydrogen, producing chemicals. Chemicals such as ammonia is a molecule that has the formula NH3. So there's one nitrogen and three hydrogens, meaning there's no carbon in ammonia. And the goal is to take renewable energy to make renewable hydrogen and renewable ammonia. That ammonia can then be a carrier for renewable energy, which we then use in engines such as this one, essentially taking renewable energy from Saudi Arabia in the form of ammonia to Japan and burn that in power plants to make electricity in a carbon-free way. And researchers in our group, we develop numerical tools, models to understand how we can burn ammonia. We also work with experimentalists to do testing in engines to make them operate on this carbon-free fuel.
We know how to generate hydrogen, harvesting renewable energy. Now the question is, how are we going to transport this energy? Already for a number of years, we are betting on ammonia as the best carrier for this hydrogen. Right? As most people know, ammonia synthesis is a process that has been industrialized for more than 1 century. It's very well known. It's already at a scale, so we can always couple it with hydrogen generation.
يبدو غاز الأمونيا بديلاً ممتازاً. إذن ما الذي يمنعنا من استخدامه؟
Ammonia, as an emerging fuel, has several issues. One has very low flame speed, has high auto-ignition temperatures, and it produces a lot of potential pollutants, particularly NOx. So what we have over here is a new burner that we're developing. We have a bluff body, which has some aerodynamic stabilization. We have an annulus of pure ammonia that has some swirl, which helps stabilize, and then an outer annulus of pure methane. And once we understand how this burner configuration, this flame behaves at 5 bar, we'll take it and put it in our gas turbine. We add pressure, the next level of complexity, and finally we put it in a practical device, which will then run to look at performance criteria, thermodynamic efficiency, and emissions. Ammonia liquefies it at 7 bar, not 700 bar or cryogenic temperature. So it's very easy to liquefy, transport, just like LPG, liquefied petroleum gas. Right? So you can easily liquefy it, carry it where you need to, and then use it at point of use. You decide, do I want to convert it back to hydrogen, split it, which takes energy? Do I want to use the ammonia directly?
Now the question is, we are going to make hydrogen, ammonia out of that hydrogen, transport it to wherever we are going to use it. The question is, how are we going to recover back that hydrogen that we have put in ammonia? This is specifically the technology in which we are focusing, and especially Jose, working here on the topic. We have developed, together with our industrial partners, a new process to reclaim back hydrogen from ammonia that makes possible to recover up to 75% of the hydrogen that was originally put on the ammonia already at 350 bar, so that you could directly fill your hydrogen car out of the hydrogen that we are generating there. We expect this technology to become already at the industrial scale, to be demonstrated at the industrial scale by 2023.
يبدو أن التقاط ثاني أكسيد الكربون نظرياً أسهل من الواقع العملي. فلما ذلك؟
The reason we are not doing it today is because existing technologies does not afford to capture that CO2 at a cheaper price. Today, CO2 capture from air, which is called direct air capture, is around $300 a ton. It has to be something around $100 a ton. And in order to do so, you need a very specific kind of a material adsorbent that can selectively capture CO2 from air. And to put that into perspective, what does it mean CO2 from air? It means you have one CO2 molecule in the air, this is 400 ppm today, and on the other hand, you have 2,500 molecules between nitrogen and oxygen. So you can imagine that you have this crowd and you want only to pick up CO2 from there. So you need a material that is highly specific to capture CO2. And indeed, I can smile about it, this is what we did in KAUST. We find a material that can actually capture CO2 from air. This material is called KAUST-7. What's unique about KAUST-7, it has a specific entrance that has actually the exact size to actually discriminate between CO2 and nitrogen. And indeed, we successfully scale up this material to kilogram scale. And now we are partnering with a third party so we can put this in a process and demonstrate it in a field where it will capture 1 ton per day CO2 as a start with the objective to have it deployed at large scale.
بعد أن التقطنا ثاني أكسيد الكربون من الجو، ماذا سنفعل به؟ في جامعة كاوست يستكشف العلماء عدة حلول، وأحدها تخزين الكربون في باطن الأرض.
Part of the key initiative here at KAUST is called the Circular Carbon Initiative, and we are working on what we call geo-based solutions. So how can you capture CO2 on the surface and store it in the subsurface? So one of the key areas that we are interested in is to understand the thermodynamic behavior of CO2. How does it behave as we change the temperature and pressure? In liquid phase here, as your temperature changes, now we can start to see how CO2 is vaporizing and going from the liquid phase to what we call the supercritical phase. We're trying to understand what happens underground. So we create this model. This is made of different sand particles, and we're trying to mimic the underground layering and formations. So we inject CO2 in the bottom, and we're trying to observe how CO2 percolates and goes through the underground formation. This will help us later on in doing our modeling and our understanding the optimum conditions to store CO2. There is different potential storage technologies. One of them is to store CO2 in deep aquifers to try to locate hydrocarbon reservoirs, depleted reservoirs, and try to use these structures because these are secure structures. They are proven structures that can contain fluids for a long time. Another area that we look at is to understand because we deal with rocks, right? We work with rocks, and we want to understand from one side the structure of these rocks at the pore scale. These rocks are solid as you see them, but there is a lot of significant amount of pores inside them. So from one side, we need to understand what's the percentage of the pore space, all right, or the pores inside the rock, how they are connected together, and also when you put fluid in them, like CO2, for instance, or other brine and water in them, where they reside and how they interact with each other.
إليكم طريقة أخرى للتخلص من ثاني أكسيد الكربون، وهي إعادة استخدامه بإنتاج الوقود الإلكتروني.
We started 5 years ago a very large program in which we were targeting one of the most feasible products out of carbon dioxide, which is methanol. And we developed probably one of the most efficient catalysts for the transformation of CO2 to methanol. This catalyst, we are at this moment working on the upscaling and hopefully will be applied in the near future. But we haven't stopped in methanol. One has to consider that we still have a lot of combustion-based cars running in the world that are going to be running for the next 20 years at least. That means that if we could find an immediate solution in making those fuels CO2 neutral, we could already save a lot of the emissions that are derived from transportation at this moment. If fuels are CO2 neutral by definition, because we are recycling that carbon dioxide, instead of allowing it to stay in the atmosphere, we capture it again, transform it into something that can be fed to a car, and then the car can run.
But also to go a bit further. The Red Sea is not just a great place for making renewable energy, However, you also have a large amount of shipping that comes through the Red Sea. You have the Suez Canal in Egypt. About 10 to 15% of all global trade between Europe and Asia goes through the Suez Canal, through the Red Sea, and over to Asia. So Saudi Arabia can be a great refilling station for renewable fuels in the Red Sea region. And our ambition is the Red Sea becomes a green shipping corridor, and one of the first green shipping corridors for the world, fully powered by renewable fuels.
It is my real dream to leave this world in a better situation than that in which it was before I arrived here. Now, as a scientist, I have the opportunity to make perhaps a bigger impact than a regular citizen, and that brings a lot of responsibility. So I will really regret if at the end of my career I haven't been able to contribute with technologies, with innovations that help solve, among other things, climate change.
الأبحاث في جامعة كاوست ليست محصورة بتلك المعنية بمستقبل الوقود. تشترك الجامعة أيضاً في مبادرة عالمية للحفاظ على الموارد بالكربون الأزرق. في الحلقة القادمة سنتعرف أكثر على مشروع الكربون الأزرق ودور البحر الأحمر فيه.